Today's lecture is going to be basically devoted to working out a single example of a nonlinear system, but it's a very good example because it illustrates three things which you really have to know about nonlinear systems. I've indicated them by three cryptic words on the board, but you'll see it at different points in the lecture what they refer to. So each of these represents something you need to know about nonlinear systems to be able to effectively analyze them. In addition, this is the, I'm not allowed to collect any more work according to the faculty rules after today, and of course I won't. But nonetheless, the final will contain material from the reading assignment G7 and I'll touching on all of these today, and 7.4, just a couple of pages of that. You'll see its connection with what it discusses the same example we're going to do today. And then I suggest those three exercises to try to solidify what the lecture is about. So I'm going to, instead of introducing the nonlinear system right away that we're going to talk about, I'd like to first explain, so that it won't interrupt the presentation later, what I mean by the conversion to a first-order equation. For that, why don't we look at, maybe I can do it here. So our system looks like this, dx dt. For once, I'm not writing x prime because I want to explicitly indicate what the independent variable is. So that's it's a nonlinear autonomous system. So there's no t on the right-hand side, but this is not a simple linear function, ax plus by. It's more complicated, like you had in the predator-prey robin earthworm problem that you worked on last night. And the other equation will be g of xy. So explicitly, this is the system, and explicitly it's nonlinear in general and autonomous, as I've indicated on the right-hand side. Now, remember that the geometric picture of this was as a velocity field. So you made a velocity field out of the vectors whose components were f and g. So that's fi plus gj. But what it looked like was a plane filled up with a lot of vectors, and so pointing different ways according to what the velocity at the point was. Then side by side with that went the solutions. A typical solution was x equals x of t, y equals y of t, represented as a column vector. And the geometric, that's a parametric equation, and the geometric picture of that was as given by its trajectory. We called it, when you plotted it, it was a trajectory. Which had not only the right direction at each point, in other words, but it also had to have the right velocity at each point. In other words, sometimes the point was moving rapidly and sometimes it was moving more slowly along that path. And the way it moved was an important part of the solution. Now, what I plan to do is the conversion that I'm talking about takes place by eliminating t. Now, why would one want to do that? T, after all, is an essential part of the solution. The way it's an essential part of this picture because without t, you would not know how long the arrows were supposed to be. You would still know their direction. And of course, it occurs in here. Now, let's take the first step and eliminate t from the system itself. Now, as you see, that's very easy to do because the right-hand side has no t in it anyway. And the left-hand side has the t only as the denominators of the differential quotients. So the obvious way to eliminate t is just to divide one equation by the other. And since usually we think of not dx by dy, but dy by dx, I will bow to what is dy over dx? Well, if I divide this equation by that equation, dy by dt divided by dx by dt, according to the chain rule, or according to common sense, you cancel the dt's, right? And you get dy over dx. And on the right-hand side, you get g of xy divided by f of xy. But what is that? That is the equation of the first day of this term. By taking that single step, I convert this nonlinear system, which we virtually never find explicit solutions to, into a an ordinary first-order equation, which, in fact, you also don't usually find explicit solutions to, except with our narrow blinders on. We only get problems at the beginning of 1803 where there will be an explicit solution to this. So I've converted the nonlinear system to a single first-order equation to which I can apply the usual first-order methods, which include hope that I will be able to solve it. Now, what do I lose? Well, what happens to this picture? If you don't have the t in it anymore, then you don't have velocity. You don't have arrows with a length to them, because the length gives you how fast the point is going. Without t, I don't know at any point how fast it's supposed to be going. All I know at any point xy is no longer dx dt and dy dt. All I know is dy dx. In other words, the corresponding picture, if I eliminate t from this picture, all that is left is the directions of each of these arrows. What disappears is their lengths. And in fact, I can't even, since dy dx is purely a slope, I can't even tell whether it's meant to be going this, the point is traveling this way or that way. It doesn't make any sense to have the point traveling anymore, since there is no time in which it can travel to do its traveling. So that picture gets changed to the direction field. The corresponding picture now, all you do is you take each of these arrows, you snip it off to a standard length, being careful to snip off the little pointy end, and it becomes nothing but a line element, and all it has is a slope. So the picture gives what corresponds to the velocity field here is now just our slope field, or our direction field. All we know is the slope at each point. How about the solution? Well, if I've eliminated time, the solution is no longer a pair of parametric equations. It's just an equation involving x and y. I can hope that the solution will be of the explicit y equals y over x, but you already know from the first days of the term that sometimes it isn't. Let's call that explicit solution. Often you have to settle for, and sometimes it's not a pain, it's something that's even better, settle for a solution which looks like this, which is y defined implicitly as a function of x. And what does the picture of that look like? Well, the picture of this is simply, it's now simply an integral curve. It's not a trajectory anymore. It's what we called an integral curve. So I'm reminding you of the very first day of the term, or maybe the second day. And all it has is, at each point, the right slope, because that's all the field is telling me now. It only has a slope at each point. It doesn't have any magnitude or direction. It has the direction, but it doesn't have any direction in the sense of an arrow telling me whether it's going this way or the opposite way. So that's the picture with t in it. These are the corresponding degeneration of that. It's a coarsening. It's a cheapening of it. It's throwing away information. Throw away all the information that had to do with t, and we're back in the first days of the term with a single first-order equation involving only x and y, with solutions which involve only x and y, with curves which are the graphs of these solutions, but again have no t in them. In effect, they are just the paths of the trajectories, whereas the trajectory is the point shows actually how the point is moving along in time, faster or slower at various points. Now, why would one want to lose information? Well, the great gain is that this might be solvable, whereas this almost certainly is not. That's a big plus. For example, let's illustrate it on a very simplest possible case. Suppose the system were, well, I can't illustrate it on a nonlinear system very well, or not right now, because in general, nonlinear systems aren't solvable. But let's take an easy example. Suppose the system were a linear one. Let's say this one that we've talked about before, in fact. That's a simple linear system, 2 by 2 system. So this means the derivatives with respect to time. Well, you know that the solutions we talked about, in fact, last time, typical solutions, which would be something like xy equals a constant times, let's say, if x is cosine t, then y would be the derivative of that, which is negative sine t. Or another one would be c2 times sine t, cosine t. And those, of course, are circles. They're parametrized circles, so they're circles which should go around, in fact, in this direction, and they have a certain velocity to them. Now, what do I do if I follow this plan of eliminating t? Well, if I eliminate t directly from the system, what will I get? I will get dy by dx. I divide this equation by that one is equal to negative x over y. Oh, well, of course, that's solvable. We're able to solve by 18.01 methods before you ever came into this course. By separation of variables. By separation of variables, it's y dy equals negative x dx, which integrates to be 1/2 y squared, dy. 1/2 y squared equals negative 1/2 x squared plus a constant, and after multiplying through by 2 and moving our things around, it becomes x squared. The nicest way to say it is implicitly x squared plus y squared equals some constant, positive constant. So these are the circles. Now, can I eliminate t? I could also take one of these solutions and eliminate t. If I square this, the best way to do it is not to use arc cosines and arc sines and whatnot, which will just get you totally lost. Square this, square that, and add them together, and you conclude that x squared plus y squared is equal to 1. Or if c1 is not 1, it's equal to c1 squared. So you can eliminate t from the solution the way you eliminate t from a pair of parametric equations, and you get in the same way that x squared plus y squared, in this case, would be c1 squared, I guess. In some sense, what we're doing is, well, we're cycling around to the beginning of the term. In fact, this whole lecture, as you will see, is about cycles of one sort or another. But I keep thinking of the great line of poetry that in my end is my beginning, or maybe it's in my beginning is my end. I think both lines occur. But that's what's happening here. This is the beginning of the course, and this is the end of the course, and they have this almost trivial relation between them. But notice the totally different methods used for analyzing this, where the t is included, than from analyzing this, where there is no t. The goals are different, what you look for are different, everything's different, and yet it's almost the same problem. Okay, now I promised you in a nonlinear example. I guess it's time to see what that is. It's going to be another predator-prey equation, but one which is in some ways simpler than the one I gave you for homework. So the predator is going to be x, and because you're used to that from the Robbins, so I'm keeping the same variables, predator-prey variables. and the prey will be y. And now just notice the small difference from what I gave you before. For one thing, I'm not giving you specific numbers. I'm going to, in the beginning at least, do some of the analysis at the beginning of the end using letters, using parameters. So I'm going to assume this is A, B, C are always going to be positive constants. I'm going to assume that x prime equals minus ax plus, so this represents the predator dying out if there's no prey there. But if there is something to eat, that term represents the predator eating the prey, meeting up with the prey and gobbling it up. And B is the coefficient, a coefficient. How about this? Well, without predators around, the prey will multiply and be fruitful. Unfortunately, they get eaten, and so there'll be a term that looks like this. Now, the basic difference between, there are two basic differences between these simple equations and the slightly more complicated ones you had with the robin earthworm equations. Namely, in the first place, I'm assuming that these guys, let's give them names just to, let's say these are sharks. I want you to be able to remember which is x and which is y. So we're going to think of these as sharks. And these will be food fish, so let's make them yummy fish. Yum fish. Okay? Now, the fact that with your robins you had a positive term here, I made this 2x, and now it's minus a times x. What's the difference? The difference is that robins have other things to eat, so even if there aren't any worms, a robin will survive. It can eat other insect grubs, Japanese beetle grubs. It can even eat, I think it can even eat seeds. Anyway, the robins in my garden seem to be pecking at things which don't seem to be insects. The other is that I'm assuming a very naive growth law, so that, for example, if there are no sharks, how do the food fish, they're fruitful and multiply, they multiply exponentially. Now, obviously, you can't have unlimited growth like that. So we added, with the worms, we added a term minus a constant times y squared to indicate that even worms can't multiply purely exponentially forever. But ultimately, their growth levels off because they can't find enough organic matter to plow their way through. So those are the two differences. I'm not assuming a logistic growth law. This is less sophisticated, and it's than the one I gave you for homework. And it also does not assume, this assumes that sharks have absolutely nothing to eat except these fish, which is, that's not so bad. That's true, more or less. Okay. Now so my plan is now, with this model, let's start the analysis as you learn to do it, and we're going to run into trouble at various places, and the troubles will then illustrate these 3 points that I wanted to add to your repertoire of things to do with nonlinear systems when you run into trouble. And we'll also increase your understanding of the nonlinear systems. So the first thing we have to do is find the critical points. Okay, now I'm going to assume that you're good at this, and therefore not spend a lot of time detailing the calculations. I'll simply write them on the board. So the first equation I'm going to write down is x times minus a plus by equals 0. And I assume you know why I'm writing that down. And the other equation will be y times c minus dx is 0. Those are the simultaneous equations I have to find the critical point. Okay, so the first one is if the product of these is 0, either x is 0 or the other factor is. So if x is 0, then from the second equation, if x is 0, y has to be 0 also. So that's one critical point. Now, if x is not 0, then this factor has to be 0, which says that y must be equal to a over b. And if y is equal to a over b, it's not 0 here, Therefore, this factor must be 0, which says that x is equal to c over d. You see right away that this must be a simpler system because it's only producing 2 critical points, whereas the system that you did for homework had 4. So here's one. Well, let's just write them up here. So the critical points are 0, 0. That doesn't look terribly interesting, but the other one looks more interesting. It's c over d, a over b. Well, let's take a look first at the 0, 0 critical point, the origin, in other words. What does that look like? Well, at the origin, the linearization is extremely easy to do because I simply ignore the quadratic terms, which are the product of 2 small numbers, whereas these only have a single small number in it. So it's minus ax cy. In other words, the linearization matrix is minus a, 0, 0, and cy gives me a coefficient c there. Now, I don't think at any point I've ever explicitly told you. I hope you've learned from the homework or maybe your recitation teachers, but for heaven's sake, if you have put this down in your little books. If you have a diagonal matrix, for God's sakes, don't calculate its eigenvalues. They're right in front of you. They are always the diagonal elements. So the eigenvalue, you can check this out if you insist on writing the equation, but trust me, it's also clear that, it's clear. If I, for example, subtract c from the main diagonal, I'm going to get a determinant, make the determinant 0, because the bottom row will be all 0. So the eigenvalues are negative a and c. In other words, they have opposite signs. This is a negative number, that's a positive number, because a, b, and c or d are always positive. And therefore, this is automatically a saddle. You don't have to calculate anything. It's all right in front of you. It must be a saddle and therefore unstable because all saddles are. And in fact, you can even draw the little picture of what the stuff looks like near the origin without even bothering to calculate eigenvectors, although it's extremely easy to do, just from common sense. These are the sharks, and these are the yumfish. Well, if there are 0 yumfish, in other words, if I'm on the shark axis, the axis of sharks, I die out. Well, forget about this side. It's only positive side, which makes sense. But I die out because the sharks have nothing to eat. Whereas if I'm on the yumfish axis, I go this way. I grow because without any sharks to eat them, the yummy fish increase. So it must look like that, and therefore the saddle must look like this. The saddle curves hug those and go nearby. Now, the other critical point is the interesting one, and for that, the analysis, in order that you don't spend the rest of this period writing A's, B's, C's, and D's, I'm going to make the simplifying assumption, but it doesn't change qualitatively any of the mathematics. It just makes it a little easier to write everything out. I'm going to assume that everything is 1. Sorry. Well, in fact, even this would be good enough, but let's make everything 1. So I'm going to assume this. And it's only to make the writing simpler. It doesn't really change the mathematics at all. Well, if everything's 1, in order to calculate the linearized system, I'd better use the Jacobian, but perhaps it would be better to write out explicitly what the system is. So the system now is x prime equals minus x plus xy, all the coefficients are 1, and y prime is equal to y minus xy. So what's the Jacobian? Well, the Jacobian is the partial of this with respect to x, which is minus 1 plus y, the partial with respect to y, which is x, the partial of this with respect to x, which is minus y, and the partial with respect to y, which is 1 minus x. But I want to evaluate that at negative 1, 1, at the point 1, 1, which is the critical point. It's the critical point because I've assumed that all these parameters have the value 1. And when I do that, I get, evaluating it at 1, 1, I get what matrix? Well, I get 0, 1, negative 1, 0. In other words, the linearized system is, what is it? It's x prime equals y, and y prime equals negative x. Well, that's just the one we analyzed before in terms of, where is it? Here. In terms of, it's the one whose solutions are circles. In other words, what we find out is that the linearized system is what geometric type? Saddle, node, spiral, none of those. It is a center. So the linearized system is a center. It consists, in other words, of a bunch of curves going round and round next to each other. Concentric circles, in fact. Well, what's wrong with that? Okay, now we're in deep trouble. We are now in trouble because that is a borderline case. Let me remind you of what the borderline cases are. When we drew that picture, this is not from this is from last week's problem set, so you have perfect excuse for forgetting it totally, but I'm trying to remind you of it. That's another reason why I'm doing this. Remember that picture I asked you about that appeared on the computer screen? Remember, this was let's make it a little flatter so that I can have room to write in. So this is a parabola, a certain parabola whose equation you are dying to tell me, but I'm not asking. So there is the trace. This is the determinant, and the characteristic equation is related to these values of these numbers, like plus d equals 0. Then these were spiral sinks. This was the region of spiral sources. That's the abbreviation for sources. These were nodal sources, nodal sinks, and these were the nodal sources. And down here were the saddles. And where were the centers? The centers were along this line. The centers, there weren't many of them, and they were the separation for these two regions. Now before, so I'll put that down. These are the centers. These other borderline correspond to other things. These are defective eigenvalues, zero eigenvalues, and so on. But let's concentrate on just one of them. You'll find the others discussed in the notes GS7. But if you get this idea, then the rest is just details. I think it'll be perfectly clear. What's wrong with a center? The answer is that if we're on a center, for example, this system corresponds to the trace being 0 and the determinant being plus 1. So it corresponds to t equals 0 and d equals 1. This point, in other words. Now, if I wiggle the coefficients of the matrix just a little bit, just change them a little bit, what I'm going to do is move off this pink line, and I might move to here, or I might move a little way to there. But if I do that, I change the geometric type. In other words, this is a sort of, being a borderline, it's a slight change of the parameters can change what it changes to. And in fact, that's geometrically clear. What does a center look like? A center looks like this. A bunch of curves going around all in the same direction, like concentric circles or maybe ellipses or something like that. If I deform that, deform the picture just a little bit, well, I might change it into something which looks like this, where after they go around, they don't quite meet up with where they were to start with. And I'm going to get a sink, a spiral sink. Or I might do the deformation by going around once and I'm finding a little outside of where I was, in which case it's going to be a spiral source. So the fact that just changing these curves a little bit can make change the picture to this or to that corresponds to the fact that if you're on here with this value of t and d, 0 and 1, and just change t and d a little bit, you're going to move off into these regions. You might, of course, stay on the pink line. It's not very likely. So where does this leave us? Well, if the linear system isn't stable in the sense that if you change the parameters a little bit, it doesn't change the type, this is, after all, only an approximation to the nonlinear system. If this approximation, you can't really predict the behavior of very well when you change the parameters, then you can't change, from it, you cannot tell what the original system looked like. So in other words, the nonlinear system might, at 1, 1, might be any one of the possibilities, still a center, or it might be a spiral sink, or it might be a spiral source. Any one of those three is a possibility. It couldn't be a saddle, because that's too far away. It couldn't be a node. That's too far away, too. But it could wander into either of these regions, and therefore, the picture, you cannot tell which of these three it is just from the analysis, this type of critical point analysis. Well, that was Volterra's problem. By the way, the person who introduced these equations and studied them systematically in the way which we're doing it here was Volterra, and in fact, he was interested in sharks and food fish, as they were called. What do we do? Well, you have to be smart. What Volterra did was he went to method number 1. Let's do it. Volterra said, okay, I got my equations. X prime equals, what was it? X prime equals, so it's minus x plus xy. Y prime is equal to, these are the food fish, so there are y minus xy. Let's eliminate t. And my problem is, of course, I'm trying to determine what type of critical point 1, 1 is, and the method we've used up till now has failed because it gave us a borderline case, which is, from that we can't deduce. Okay, so he said, let's eliminate t, and we get dy dx equals y, I'm going to factor, y times 1 minus x on top, and on the bottom, factor x, negative 1 plus y. Okay, you could solve that before you came into 1803, right? This, you can separate variables. Ha! Ta-da! Let's separate variables. Okay. So the y's all go on one side, so y goes down here. So it is y minus 1 over y dy equals, on the other side, it's the dx gets moved up, 1 minus x over x dx. Now, of course, you wouldn't dream of using partial fractions on this. It would be illegal because even though it's a rational function, the quotient of two polynomials, the degree of the top is not smaller than the degree of the bottom. In other words, this degree, to partial fraction it, this degree must be bigger than that one, and it isn't. So you have to first divide, and if you divide by that, then there's no point in using partial fractions at all. Of course, you would have done this by basic instinct, I know. So what's the solution? It is y minus log y equals log x minus x plus some constant. That's not the final constant I want, so I'll give it a subscript 1 to indicate I want more. Now, this is very hard to see what that curve looks like. We can make it look better by exponentiating. If I exponentiate it, going back to high school mathematics, but I know from experience many of you are not too good at this step. That's another reason I'm doing it. It will be e to the y, that part is easy, times, because pluses and minuses change into times, e to the negative times e to the negative log y. Well, e to the log y is y. If I put a minus sign in front of that, that sends it into the denominator. So instead of being y, it is 1 over y. Equals x, e to log x is x, e to the negative x is therefore times 1 over e to the x. And that's times the exponential of c1, which I'll call c2. And now if I put them all on combine them all into put them all on the one side. It's x over e to the x times y over e to the y is equal to yet another constant, 1 over c2. Let's call, this is my final constant, so let's call that c. In other words, the curves, the integral curves are the graphs of this equation for different values of the constant c. Well, of course, you know, you've graphed an equation like that all the time. What am I going to do with this stupid thing? Well, the first thing, so I deliberately picked something which involves all your learning up till now. So now we are now going into 18.02, right? You looked at that at 18.02, you would say, this is the contour curve. These are contour curves of the function. Well, let's write it out the other way. It doesn't make any difference, but just you're more likely to have seen the function in this form than x over e to the x you won't recognize, but this you will recognize. In fact, we've had it before in this term. It's one of the kinds of solutions you can have to second-order equations. Times y e to the negative y equals c. How does this, so it's the contour curves of this function. Let's call that function, let's say h of xy. Well, of course, you could throw it on MATLAB, as you did in 18.02, maybe, and ask MATLAB to plot the function, but Volterra didn't have that luxury. He was smart, too, so let's be smart instead. What is the function x? Let's use a neutral variable like u and plot u e to the negative u. Okay, 1801. At 0, it has the value 0. When u is small, this has approximately the value 1, and therefore it's like the function, starts out like the function u. As u goes to infinity, you know by L'Hopital's rule that this goes to 0. So it ends up like this. Well, what on earth could it possibly do except rise to a maximum? But where is that maximum? It's easy to see there's a unique maximum just by 1801. Take the derivative, find out where the maximum point is, and you will find, perhaps you've already done it, that this is at 1. The maximum occurs at 1, and the value, that's where the derivative is 0, and the value there is 1 times e to the minus 1. It's 1 over e, in other words. That's what the curve looks like. What do the contour curves of this look like? Aha. Well, so if we're looking at the contour curves of the function h, so here's x, here's y, and we want the contour curves of the function h of xy, what do I know? Where is its maximum? The maximum point of h of xy is where? Well, h is the product x e to the negative x times y e to the minus y. This has its maximum at 1. This has its maximum at 1. So where does h of xy head? Well, you can't make any. You got two factors. One makes each of them the biggest it can be. The maximum must be exactly at that critical point, 1, 1. So that's our maximum point. Let's give it a, make it conspicuous. Ta-da. So this is the maximum point. The point, it's the point 1, 1. It's the point which makes everything, makes the function biggest. Now, how about the contour curves? Well, this is the top of the mountain. What is it along the axes? Along the axes, when either x or y is 0, the function has the value 0. So it's biggest there. It has the value 0 here. So it's 0 value. What are the contour curves? Well, we must have a mountain peak here. This is the unique maximum point. In fact, it's easy to see the contour curves just surround it like that. Now, the reason they cannot be spirals, for first place, you've never seen contour curves which were spirals. That's a good reason. It's a mountain, you know, that's the way contour curves of a mountain look. But all right, that's not a good argument. But notice that along each horizontal line here, I want to know how many times can it intersect the contour curve. That's the same as asking along one of these lines, how many times can it intersect? See, this is a graph of the function along this horizontal line. And therefore, how many times can it intersect one of the contour curves? The same number of times that it can intersect a horizontal line can intersect this curve twice. Only once if you're exactly at that height, and after that, never. Okay, so, but here it can intersect each contour curve only twice, which means these things cannot be spirals. Otherwise, they would intersect those horizontal and vertical lines many times instead of just twice. So that's what it looks like. In fact, we can even put in the direction without any effort. We know that the sharks die out without any food fish, and the food fish grow. Well, I think this has to be clockwise. You know, because the guys nearby must be going the same way, and therefore the guys near them must be going the same way, and therefore the guy, you know, it's sort of a domino effect. It spreads, the direction spreads, and there's only one compatible way of making these. They all must be going clockwise. So what's happening actually? The food fish start. At this point, there are a lot of sharks, but not so many food fish. The sharks eat the few remaining food fish, and now the sharks start to die out because they got nothing to eat. When they're practically gone, the food fish, hey, we can start growing again. And they grow, and meanwhile, for a while they grow happily, and then the sharks suddenly start being able to find them again, and the few remaining sharks start eating them. The population of sharks grows, the food fish start dying out again, and the cycle starts all over again. Now, I wanted to talk about the qualitative behavior. This is, in some ways, the most important part of the lecture. I want to discuss, just as we did at the beginning of the term, the effect of fishing. Of fishing with nets at a constant rate k. Just as at near the beginning of the term, we talked about fishing a single population. The only difference is now there are two populations, both sharks and the food fish. Now, what happens to the equations? Well, x prime is equal to, the equations start out just as they were. I'm now reverting to a and b because, well, you'll see why, because we need the general coefficients, plus bxy, but if we're fishing with nets, then a certain fraction of the sharks in the sea get hauled in by the net. And the fishing rate, say the fishing rate is k, means we remove, there's a fishing term, we remove minus k times the number of, a certain fraction of the sharks in the sea. How about the food fish? Well, we remove them too. And we don't distinguish between sharks and food fish, so this is cy minus dxy, but we also remove them, a certain fraction of them, minus k times y. What, therefore, is the new system? The new system is, therefore, x prime equals minus a plus k. I'm combining those two x terms, plus, that's times x, plus bxy, and the y prime is c minus k times y plus minus dxy. So in other words, now to solve these, I do not have to go through the analysis. All I have to do is change the numbers. Change these coefficients from a to a plus k and c minus k. Now, what's the new critical? The old critical point was the point c over d, a over b. The new critical point with fishing is what? Well, the parameters have been changed by the addition of k. So the new critical point is c minus k over d and a plus k over d. So what's the effect of fishing? Well, if the sharks here, if the old critical point was over here, let's say this is the point c over d, and this is the point a over b. That's the old critical point, was over here. The result of fishing is to lower the value of x and raise the value here. So the new critical point is this gets lowered to c minus k over d, and this gets raised to a plus k over b. In other words, the new point is there. So the effect of fishing is to, it does not treat the sharks and the yummy fish equally. The effect of fishing is lowers the shark population. See, the critical point gives sort of the average shark population. Average shark, of course, it cycles around these, but on the average, this gives on the average, how many sharks there are and how many food fish there are. So the new critical point with fishing lowers the sharks population and raises the food fish population. That's not intuitive, and in fact, that was it was the observation that was observed experimentally in a slightly different context, and that's why Volterra started working on the problem. If you'll give me, I will need 3 more minutes. The most interesting application of all is not to sharks and food fish. I can't assume that you're dramatically interested in how many of them there are in the ocean, but you might be more interested in this. Because this same, it's called, that thing about lowering is called Volterra's principle. Put that in your books. Volterra's principle. Volterra is spelt over there. All right, Volterra. Has found more modern applications than sharks. Suppose you consider fish in a pond. You have mosquito larvae, which breed in the pond. Oh, well, what happens, this happens, and then suddenly there's a plague of mosquitoes, and so concerned citizens, and this is what happened in the 50s. That was before you were born, but not before I was born. What happened is, with a lot of mosquitoes, so everybody said, well, the mosquitoes breed in the little stagnant ponds. Spray DDT on them. DDT them. Dump it in the ponds. That will kill all the larvae, and we won't get bitten anymore. Now, when you put DDT in the pond, as people did not realize at the time because they were, these things were new, of course you kill the mosquitoes. But you also kill the fish because DDT is poisonous to fish. So what in effect you're doing is exactly, mathematically, it's the same as harvesting the fish population with the sharks and the food fish. The result is if this is the fish are the predators because they eat the mosquitoes. They eat the mosquito larvae, big food. If there was a certain equilibrium, according to Volterra's principle, with DDT, that equilibrium moves to here. In other words, the effect of indiscriminately spraying the pond with DDT is to increase the number of mosquitoes and kill fish. And in fact, that's exactly what was observed. The same thing was observed with the bird population and insects. Spraying trees for insects to get rid of some pests ends up killing more birds than it does insects. And the insects increase. Thanks.